Good evening. Today we are going to see one more problem, that is of compound bar. But here today we are going to see bar with one end fixed and other end free. Now I have this channel, Civil Engineers Technical Hub, and in this channel you can have different playlists and videos related with that subject are in this playlist. So you can go through it and you can see videos related with that subject. Subscribe channel Civil Engineers Technical Hub so you will be updated with the new uploaded videos. So now we have this question was asked in SPPU examination. So a mild steel 3-stepped rod of diameter 100 mm, 80 mm and 60 mm of E200 GPa and length 200, 200 mm and 150 mm from the first end. One end is fixed. So this is most important. Diagram is not given. You have to plot the diagram. Is fixed and other is subjected to axial tensile load of 25 kilonewton. Model the rod with 3-stepped rod and solve the following by FEM. We have global stiffness matrix, the nodal displacements and reaction forces. So now the diagram, if we will plot, we have 100 mm diameter first, second we have 80 and third 60 because this is given stepped rod. Now length of first two are 200 and last one we have 150 mm and force applied is 25 kilonewton. So this is given. We have to draw the diagram. Diagram is not given. Now first we will give notes. So we have one and the other end we have two. Always it is preferable first give primary notes and then go for secondary. Then here your diameter is changing, so will be given third. Here also diameter is changing, so given it as fourth. So we have these 4 nodes and connecting these 4 nodes, we have 3 elements. So we will show that elements also we have A, B or member connecting to 1, 3. This will be my first element. Then 3, 4 we have second element and CD we have third element. So we have 4 nodes and we have 3 elements. Now we are going to solve the problem. So already we have solved one problem where we have both end fixed and now here we have one end fixed. So now we have stiffness matrix for element 1. As we know, stiffness matrix for axial member we have AE by L 1 minus 1 minus 1 1. And then we will go for first element. We have A1 E upon 11 and then we have diameter as 100, L as 200 and E is given 200 GPa. So 200 into 10 raised to 3. So we have pi by 4 into 100 square. This is value of E 200 into 10 raised to 3 upon 200, 1 minus 1 minus 1, 1. If we will solve this, then we will get it as 7.85 into 10 raised to 6, 1 minus 1 minus 1, 1. So this is for element 1. Then we will go to element 2. Now we have 80 mm diameter, length we have 200. So K2, if we will write, then A2E upon L2, 1 minus 1 minus 1, 1. And then we will substitute value pi by 4 into 80 square into 200 into 10 raised to 3 upon 200, 1 minus 1 minus 1, 1. And if we will solve this, we will get value of this that is equal to 5.03 into 10 raised to 6, 1 minus 1 minus 1, 1. So this is K2. Now I am not taking yet any values that is constant outside because we have to find out which will be smaller one. And now I will go with 3, K3, A3E upon L3, 1 minus 1 minus 1, 1. Diameter we have 60, so 60 square, and then we have 200 into 10 raised to 3. Now L for third member is 150, and this will gives us this will gives us value that is K3, and that is 3.77 into 10 raised to 6. So we have 3.77 into 10 raised to 6. This is smaller in these three. So we can see this. We have K1 7.85, K2 5.03, and K3 3.77. Now minimum we have 3.77 into 10 raised to 6. So this we will keep outside, and then remaining values we will take inside. Means we have to divide this by 3.77. We have to divide this by 3.77, and whatever value will be there, we have to take that value inside. Means we have to multiply these elements with that value. So K1 we will get, so this value I will get it as 2.08. So this will be 2.08. So we will multiply 2.08 minus 2.08 minus 2.08 and 2.08. Now for K2, we have this value that is 1.33. Means we have this value that is 1.33. We have 10 raised to 6 over here. So this actually gets cancelled in both the cases. And then we have this will be 1.33 minus 1.33 minus 1.33 minus 1.33. And now we have to go for global stiffness matrix. K3 will remain as it is. And we have to go for global stiffness matrix. Now we have this will be 1, this will be 3, 1, 3. And therefore we will get this as 1, 1. This we will get as 1, 3. This will be as 3, 1. And this will be as 3, 3. Then we have this will be 3, 4, 3, 4, and we will get it as 3, 3, as 3, 4, and this will be as 4, 3, and as 4, 4. And last we have that is this is K3 I have mentioned. So actually that K1 we have over here. So I will just repeat it. Actually, not this one. We have to start with this. So this is 3, this is 4, this is 3, 4. Then we have this value that is 1, 3, 3, 4. So 1, 3. Then we have this value as 3, 4, 3, 4. And this will be 4, 2, 4, 2. So that we have to correct it. Then this I will get as 1, 1. This I will get as 1, 3. This will be as 3, 1. And this will be as 3, 3. So actually this was considered, but this is the third one. So we have below. Then we have this will be as 3, 3. We have as 3, 4. This will be as 4, 3. And as 4, 4. And then this will be last as 4, 4, as 4, 2, as 2, 4, as 2, 2. So we have as 4, 4 this element, as 4, 4 this element, and then as 3, 3 this element, and then we have as 3, 3 these elements. So 2.02, 1.33, 1.33, and 1. So you can see we have this will be global stiffness matrix. So this will be for first element. So first element. So remaining we will get 0. Then this is for second element. So we have this is second element. And then we have third element. So that is third element. And then remaining value are 0. So we have these are 0. And now if we will calculate global stiffness matrix, so we will have this as global stiffness matrix. So this is first answer. So global stiffness matrix. Global stiffness matrix. And we have this global stiffness matrix values. Now once I know global stiffness matrix, then we have to go K, F is equal to K into delta. Now K is stiffness matrix, F force, and D we have displacement. Now we have this as one end fixed, and therefore what we will get if we will see the diagram, we will go little bit back and you will see this diagram. So we have in the diagram, So here we have reaction. We are always considering positive direction. This will be R1. Here we do not have any force, so we have value 0. At 4 also no force, 0. And at 2 we have 25 plus because it is towards positive. And then we have to put that value in that equation, and we will get this as R1 0 0 25 into 10 raised to 3. 3.77 into 10 raised to 6 into this value, which is your global stiffness matrix. And we have four displacements that are at four nodes, which are U1, U2, U3, U4, and U2. So 1 and 2 are primary nodes, and 3, 4 are secondary nodes. Now we know we have this U1 value that is 0 because we have fixed end. So we have to remove first row and first column. And then we will get it as 25 into 10. Sorry, we have this as 0, 0, 25 into 10 raised to 3 equal to 3.77 into 10 raised to 6. And then we have 3.41 minus 1.33, 0, minus 1.33, 2.33, minus 1, 0, minus 1, 1. And on this side we have U1, U2, U3, U4, and U2. Now we can frame the equation also, so we will get it as 3.41 U3 minus 1.33 U4 plus 0 U2 equal to 0. Then minus 1.33 U3 plus 2.33 U4 minus U2 equal to 0. Then 0 U3 minus U4 plus U2 equal to 25 into 10 raised to 3 divided by 3.77 into 10 raised to 6. And to solve these three simultaneous equations, you will get value of U3 3.19 into 10 raised to minus 3 millimeter, U4 8.17 into 10 raised to minus 3 millimeter, and U2 0.015 millimeter, or you can write it as 15 into 10 raised to minus 3 millimeters. Knowing these values, we can find value of R, and we will get R, you can see. So we have this R1 is equal to, we have to multiply 2.08 into U1. It is 0 because U1 0, minus 3.77 into 10 raised to 6 minus 2.02 into U3. U3 we have calculated. Then 0 U4, 0 U2. So we have only one term, 3.77 into 10 raised to 6 minus 2.08 into U3. And that we have considered over here, 3.77 into 10 raised to 6 minus 2.02 into 3.19 into 10 raised to minus 3. And this will give us minus 25.01 into 10 raised to 3 Newton as a reaction. So minus 25 kilonewton, as this is minus, so we have this reaction 25 kilonewton towards left. So we have to solve this for one end fixed and other free cantilever compound beam in this way. So now we will stop here only. Thank you. जर व्हिडिओ आवडला असेल तर लाईक करा आणि सिव्हिल इंजिनियर्स टेक्निकल हब चॅनलला सबस्क्राईब करा. थँक्यू.